Thank you. Maybe you can try share your slide.
Yes, just a moment. Yes. Share only present screen.
Can you open your camera, Prof?
Just one
Okay.
moment. I think just a moment to set up.
Yeah, no problem. It's good to see you for first time, Prof.
Yes, I am fine now. Now it's available to see the camera and the PowerPoint presentation.
Class, can you see the slide, the screen right now?
Yes,
Doctor.
yes.
Yes.
Yeah, Alhamdulillah.
I am ready now.
Okay. We have here Dr. Sofyan as
I
well.
welcome Dr. Sofyan.
Dr. Sofyan, can you open your camera?
Assalamualaikum.
Walaikum assalam wa barakatuh, Dr. Sofyan.
How are you, Prof?
Fine, it's okay. I am fine. I hope that you are fine.
Yeah, I'm fine here. Okay, Dr. Saila, we can proceed lecture, isn't it?
But before
Just
that, yeah.
Customize the presentation, yes.
Okay, yeah. Can you set full screen, Prof? For the slideshow?
Oh, yes, just a moment. It's nice to have this, but I hear that you have many mics. It's opening. Maybe just mute all mics to keep the sound as clear.
Yeah. But we still cannot see the full screen.
Full screen. Yes.
Okay, it's good.
Yes.
Okay.
Thanks, Dr. Suhaila and Dr. Sofyan, for this chance to keep cooperation with your site. Today, we can go with some fundamental about stiffness matrix for frame structure. Just testing, it's clear for my voice and in my presentation.
Yeah, clear?
Yes, that's a good chance. Let's go to the next slides. Our lecture today about matrix analysis methods for frame structure and its applications with the cooperation of Dr. Suhaila and Dr. Sufyan. And I hope we keep this cooperation for the future, inshallah. This is the first step, and maybe it will be more lecture, inshallah. Just now we go with some definition. Matrix analysis or matrix methods, it's approach for computer structure analysis commercial software, or either your own software for structure analysis. As we know that during our previous study, we go with a conventional structure analysis by hand calculations. These are for structure analysis and structure statically indeterminate or determinate. And our study it was limited for simple structures, either beams or frame or trusses. Once the size of the structure going higher, our hand calculation become unmanageable. So it's difficult to continue with hand calculation. So the size of the structure is limited for hand calculation. Another approach is the statically indeterminate structure. We have different approach, either force methods or slope deflection or three moments, and each method has its complications. Another point is some assumptions that we should only limit it to rigid supports like roller or hinge or fixed. However, we don't. It's difficult to go with elastic supports or semi-rigid supports. That's some limitation for hand calculations. So we now try to make the approach for computer or commercial software. The matrix method is the first step. In fact, we have two approaches, the stiffness methods and the flexibility methods. Today, we focus our stiffness metrics and in some textbook called displacement methods. It's applicable for any kind of structure, either one-dimensional structure, beam, frame, trusses, or two-dimensional like shells elements, or three-dimensional. But today we just go with one-dimensional structure, its frame especially. During this course, just we could know or revise our knowledge about hand calculation or classical methods and what is the open window for the matrix method. Just one moment. Oh. For hand calculation, we should go with simple structures, simple loading. But with the matrix analysis computer, we can go with complex structure or complex loading. Also, for the classical method, we only limited to rigid support. However, and with the matrix methods, we can extend our analysis for flexible supports, and we will go with this definition later through our lecture. Another point is the mathematical model. How to select or to make the structure system. And this is point we will try to teach during our lecture. Another topic is linear or small deformation. Until your graduation from the bachelor degree, your structure analysis is limited to linear analysis and the small deformation. That means the structure under load, you have deformed structure. This deformed structure, it's assumed as it is the original structure. This is valid only for small deformation. But for large structure with large stadium, like roof of stadium or long span bridge, the deformation is not small. So the geometry after loading is different from the original geometry. That's one point is, or one open window using matrix analysis. Another point is the classical methods mainly focus with elastic material. But with matrix analysis, we can extend our analysis for plastic material. Different loading, either statics, that's our classical methods. But with matrix analysis, we can open all these windows. So let's go to the next. So the advantage of our matrix methods, it's formal. That's valid for all kind of structure with the same systematic proceeding. Computer friendly, and the calculation can be performed efficiently. Suitable for large structure. It's open for any size of structure. Applicable for statically determined and indeterminate with the same process and proceeding. But for a classical method, you should have different method of analysis, different approaches that make the analysis is difficult. Easy to be programmed. However, disadvantage is need more calculations. You should know about discretization and the formulation of the different elements, like curved beams or solids or something. The learning outcomes, we should know about mathematical modeling, learn how to apply any commercial software, whatever the name of this software, but we should know the technical terms. So you can go with any software, whatever the production company of this software. Another point, how to read the output of this commercial software and explain if it's logic or unlogic. Another point is the assumption and its limitation. And we will pay your attention during our lecture about these points. The flow chart of the matrix analysis. We should now first define our structure, either a frame or a truss or beams. So this is the unit that will be used to build our structure. Once we should formulate the stiffness matrix of the unit, we go to the global matrix. It's the structural stiffness matrix. And we have magic equation that solve all the structure, either truss or frame or beams, 2 dimension, 3 dimension. It's the force equal stiffness multiplied by D. And in this equation, we will try to find displacement and reactions, and then we can go with the internal force. This is the approach in a simple flow chart, and we will apply to the frame today. During this magic equation, as a structure analysis, we should keep our fundamental. The equilibrium equation should be valid. Computability equation should be valid for the displacement. The material constitutive equation that relates the stresses to the strain should be valid. And with this is 3 fundamental will be built in the matrix equation that F equal K multiplied by D. Our reference will be the textbook of Hebler, structure analysis, structure analysis 10th edition. Even I have some concern about how to the proceeding, and I will highlighting this topic. The main points for the stiffness matrix analysis for any structure, whatever this structure, either truss or frame or beams. First, we should subdivide any structure to its discrete finite element. Then define the nodes and the members. For each member, we formulate the stiffness matrix and go with the global matrix. Then solve for kinematic indeterminacy and define the reactions. This is the introduction. I will go to the subject only. In fact, any structure in physical condition is solid structure, but with our assumption that the cross section dimension is relatively small to the span of the beams, we have one-dimensional element. Another approach is for the two-dimension element. If we have one dimension is z direction is small, then in this case we go with two dimension. Our focus is in one-dimensional beam or frame or truss element. You follow with me, Dr. Swai?
Yeah, Prof.
Yes. So our concern today is the one-dimensional element. As you see that the element with the cross section now like that with the width, beam width, so beam depth in this case is B, and this is the span. So physically, this element has three-dimensional, but with the assumption that the width of the beam and the depth of the beam is relatively small to the span. In this case, we go with one-dimensional element, like a line. However, this one-dimensional element is the unit, half degree of freedom. If we plot the axis, usually x-axis is adhered to the center line, and the y is vertical, and z is out of plane. So in this case, we have three axes or three directions. If we go with the analysis of this element, so we have three forces, one in each direction. This is Fx, Fy, and Fz. This is three forces. And also we have three moments, moment about X, moment about Y, and moment about Z. So now we have 6 components of forces. 3 is force, and 3 is moment. And we should, for these forces, keep the statics fundamental. that the equilibrium should be valid. In the other side, we go with the kinematics because we have a force. Says each force has corresponding deformation as a result. So the force have displacement is straight line, and the moment is have a rotation. So for the x force we have this displacement in x direction, displacement in y direction, and displacement in z direction. This is three displacement: ux, uy, uz, z. And we have, this is corresponding to the forces. We have also three rotation: theta x, theta y, theta z. This six deformation, either displacement or rotation, called degree of freedom. And when we build our structure, whatever this kind of structure, either a truss or frame or beam, we should keep the three displacement compatibility. That's one of the fundamental of the structure analysis. This is the second concept. The kinematics is the deformations, and the static is the forces. They have some relations. That's the stiffness matrix. That's we looking for. And in our, this is for the 3-dimension, and this is the general case. We try to simplify these relations. For example, for the truss, only we have two displacement. We don't have any kind of rotation. So we can reduce this, either the forces or the displacement, to only two displacement. For the 2-dimensional, we can reduce the forces to for fx, and fy is the shear and the moment. So the 6 component in the 3-dimension coming down to 3 component for the 2-dimensional structure. This is around 50% effort saving. Another, for the kinematic, we have only horizontal displacement, vertical displacement, and rotation. This is 3 degrees of freedom. This is the case of frame structures. That's our focus today. For the frame structure, we have two partners. The normal force, this is one side, and the relation between the forces, this is the force, normal force, and the corresponding displacement u in this along the axial direction is called the axial stiffness. And I think Dr. Suhaila during the previous lecture give you this simple relation. It's equal the nodal forces. Node, this is the start point, is the end point in the x direction, and the displacement, and it's related with the stiffness matrix first. And this is the local stiffness matrix. Another point or another side is, before we go to the shear and the bending, this is the frame element. Just one moment. Oh, yes. Better. The normal force, this is one side. It's a part of the frame element. The frame element includes the normal force and the shear and the bending. And totally, we have 6 forces, 3 in each node, 3 in each node. It's the force in X direction, the force in Y direction, and the moment. And the moment, this is only one component of moment. So it could be called moment. But however, it's actually, it's a moment about Z axis. And if we list these forces as a forces over this element, so this is Fx, Fy, and the Mz. This is at the start point I. So this is, sorry, this mouse I. Only this is 3 forces. It has also them exist at the end point. So it Fx, Fy, and the moment at the end node J. So this is called the force vector. In the other side, with the kinematics, we talk about the corresponding deformation. Is deformation in X direction, deformation in Y direction, and rotation. This is at the end start point, the same for J. This is called displacement vector. The relation between the kinematics, the displacement, and the forces, it's called the stiffness matrix, That's our scope today, to find the stiffness matrix. The stiffness matrix could be the black box of the element. Have the material representative. That means the element of the structure could be from concrete or steel, whatever the kind of material. So the material here is represented by Young modulus. The other side is the cross section. The cross section have dimension, whatever the shape of the cross section. We should calculate the properties of the cross section. It's either an area or an inertia or bipolar. For the normal force, the representative of the cross section is area. The area here. Also, the geometry of the element, the distance between I and J is L. This is the overall geometry. So this constant, this value collect all the element information, either materials or cross section or the geometry or overall geometry. Now for the normal force with this simple equation, stiffness matrix equation, just expanded to frame. So the position of normal force is related to degree of freedom 1 and 4. Just one moment. For the normal force, so the degree of freedom reserved for the normal force is 1 and 4. So the position of the stiffness matrix either horizontal 1 and 4. This is the position of the normal force. Also for the vertical direction, 1, 1, and 4. This is the position of normal force. And so in this case, the normal force have 4 elements. E o A over L minus the same value, positive the same value. This is the stiffness matrix that are here. So in this case, the normal force have its position over the stiffness matrix. The row and the column will be reserved by zero value, either in the horizontal direction and this is the vertical direction. So this is the matrix of normal force in the expanded version of frame. Next step, we go to the shear and the bending. The shear and the bending, as Dr. Suhaila in the previous version, the stiffness matrix is 4 by 4, and it's you could memorize it's E, it's material, I is the moment of inertia, is the cross section, and the over L is cubic is the geometry, and it could be 4 by 4 is a 12 or 6L. Either this is a 12, 6L. This line is reserved for normal. So skip, so 2 minus 12, and 6 over EI over L decree. Then go with filling all the position. So this space is reserved for shear and bending moment, and it's 4 blocks. Each block is 2 by 2, and it's coming from the stiffness matrix of the beam for shear and bend that originally 4 by 4 divided equal 4 bars. So each block is 2 by 2. Just drop each block in each position. We get the stiffness matrix for the frame. However, this stiffness is called the local stiffness matrix. The local stiffness matrix. It's easy to memorize the stiffness matrix. As we see, that is normal, either in the horizontal or the vertical, and the others, the blocks, 4 blocks is this is shear and bending. How to use this stiffness matrix for structure analysis? For this stiffness, the local stiffness, keep the x-axis along the center line of the beam. This is the main fundamental that, oh, sorry. So this stiffness matrix could be go for beam structure with normal force. So the frame is the stiffness matrix could solve for normal shear bending. For example, if we have beam like fixed here and the roller like or hinge like that. Before we use stiffness matrix for shear and bending, that it's size 4 by 4. However, if we have, this is limited for vertical load only. But if we have inclined loads that could result in normal force or inclined supports, we have supports. In this case, the beam structure enters the cluster of frame structure. And in this case, the local stiffness matrix could be used to solve the beam. We can go with some examples. But for the frame in general, we have many elements, at least 2 elements or more. Each element has its own directions. So the problem is that when we assembly the structure in this case, if we keep the local approach, it will be difficult for the user to make the equilibrium equation or the compatibility as the connections. For example, if we have a frame like that, this is fixed here, fixed here. This is only for 2 elements. If we go with the local stiffness matrix, the element number 1 have his own forces direction. The x-axis is along the member, and the shear is in the transfer direction path. If we go with this, the second member, yes. This member has his own normal force and shear. The problem if when we go to this joint, that the member sharing the forces, the equilibrium should be satisfied. The compatibility of deformation should be satisfied. The problem with local directions, it will be difficult task to finish this conflict in this point. So in this case, I am going with the global axis. The member as individual, the member can go with the directions, x-axis along the axis, and y in the transfer direction. But when I go with a structure with many members, all the members should share a one axis system. Mainly is horizontal and vertical. In this case, the member should transfer his own normal force and shear to horizontal and vertical forces. And this is a geometric relation purely depending on the angle with the x-axis, is x-axis. For example, now we try to find this relation between the forces in the local axis to the global axis, and this relation is valid either for forces or for deformation. It's a function of sine and cosine of the angle with the x-axis. This is called transformation matrix. A transformation matrix. This transformation matrix, depending on cosine and the sine, theta x and theta y. And the computer software is automatically calculated the Cartesian coordinate difference in x direction over the span, and the difference in y-axis over the span, it's given lambda x and lambda y, that called cosine direction cosines. For the horizontal and shear forces, this is the same relation as a truss. Is the relation between local is member wise and the transfer direction as horizontal and the vertical directions. This relation is lambda x minus lambda, the lambda y lambda x, and this is direction cosines. I think you have this practice in the truss. For the frame, we have another component of the moment. The moment is around the axis, out plane axis. It's the same. So there is here this 0, 0, and the 1. That means the local moment is the same as the global moment. So the problem that Only I am concerned about normal and shear along the member and perpendicular to the member, horizontal to vertical. This is valid at the start point and as an end point. The start point is here, and the end point is here, and both of them is independent of each other. That means the start point not related to the second point, and the second point is not related to the first point. And this is the transfer matrix. It's 6 by 6. And the determinant of this matrix is equal 1. It's function of geometric function, and its value is equal 1. So if we go with the inverse of this transfer matrix, it's almost equal the transpose of the matrix. That means if we take the horizontal row line and rewritten in the vertical direction, this is almost the inverse of the transfer matrix. We go to the next step. So now we try to formulate the final. This is the details. Only you should know about the fundamental, how it's come. But finally, we go to our final destination, is the stiffness matrix. The stiffness matrix. It's originally coming from that our magic equation. It's force equal K, it's equal K multiplied by D displacement. And this equation is valid for the element level, one element, or for the structure. Of local, it's valid, and the global is valid. But how to divide? For the local, we will mark it as local in this case, in this point. The local, if we have this member, so either the displacement or the forces, the direction is along the member, perpendicular to the member, and the moment, this is the forces, it's the left side. For the right side, for the displacement, we have axial deformation, deflection along the lateral, and the rotation. And the stiffness matrix for the local, that's here. This is a stiffness matrix. And this is valid for beam, and we can go with. But for the frame with many members, the problem that each member has his own concern with his own axis, that make me a lot of trouble at the joint to make the equilibrium or the compatibility of deformation. So in this case, as a solver, I force all of them to go with my global axis, X and Y, mostly horizontal and vertical. In this case, all the members, whatever the number, I only, as a coordinator or a solver, I accept from them horizontal force and the vertical force. So in this case, when I go to the joint and to make equilibrium, it's my easy task now. I have all the forces horizontal So algebraic summation, it's okay. I have all component, vertical component, so it's easy for me to make equilibrium. Also for the deformation, I have all the deformation is horizontal or vertical, whatever the number. It could be at this node, could be 2 or more members. So my task as equilibrium or compatibility of deformation, once I force the structure to go with the global, it will be an easy task. So in this case, we go with the global matrix. The local matrix, the local forces here, or the displacement matrix, displacement here, could be substituted by transformation, as could be here. Yes. This is the relation. Just one moment. Now let's start now. We have now, this is the local stiffness. We know want to shift to global stiffness with the same concept as you study in the truss. We take this local and substitute with transformation matrix multiplied by global displacement, and you go to with the force and substitute with transformation matrix with the global force. So this equation will be T multiplied by F, and F in this case is horizontal and vertical, equal the local stiffness. It's at this moment is the same, d over hyphen. So we will change it to T multiplied by D. And the D in this case is the degree of freedom in horizontal and vertical direction. Now, what is I am looking for? To find the relation between global force and the global displacement. So if we multiply by T minus 1 for the two sides, so in this case, the matrix multiplied by its inverse, so it will be unit matrix. So the left side will be F, and for the transformation matrix, the T minus 1, it's equal T transpose, because this is a characteristic of the geometric function. So T minus 1 here, it could be a transpose multiplied by local stiffness multiplied by T, and this is the global stiffness matrix. This the main relations that we looking for. This is 3 bars term. If we multiply, it's called a global stiffness matrix that we have here. Finally, the magic equation if equal K multiplied by D. For global, it's our axis is horizontal, vertical, either for forces or for displacement. And now we should go how to find K. Just multiply T by K of hyphen or T transpose. We get the transformation maths. It's not easy to memorize, but we will try at formulate by Excel sheet or have some special condition for this. So this is a global stiffness matrix for a member with direction x-axis here and y is x-axis. So in this case, if we have this member, this is the start point, this is the end point. So in this case, this is the stiffness matrix. It's the relation between forces and displacement. And it could be a black box. And it's a function of material, cross sections, and geometry. Geometry includes the length of the member and the angle theta x that we go with the cosine directions. Lambda x is equal cosine theta x. And you have lambda y, it's the, here is theta y here, and cosine theta y is lambda y. And for your knowledge, theta x and theta y is have summation of 90. That's mean theta x plus theta y equal 90. So in some books, they only use one angle, is with theta. So cosine theta is lambda theta, and cosine y we can substitute with theta y by 90 minus theta x. So if we go with the cosine of this angle, cosine 90 minus theta x, it's equivalent to sine theta x. So in this case, we only calculate one angle with the x-axis, and we go with the geometric function, either cosine and sine. Next, this is when we go with the global axis, global stiffness matrix. This is for one element. For the structure like that, we have many elements. Each element have the stiffness relation. For example, AB member, if we go as a separate member individually, we have normal force, shear bending at A, and the same at B. This is the forces. Also the kinematic, displacement X direction, displacement in Y direction, rotation, and the same at the end point. The relation between the forces and the deformation is our global matrix. Global matrix. This is the global matrix. We have two special members. The horizontal member and the vertical member. The horizontal member, if we go with theta x equals 0, this case lambda x equal 1 and lambda y equal 0. In this case, if we go to this stiffness matrix with lambda x equal 1 and lambda y equal 0, this global matrix will be equivalent to local matrix. It is a local matrix. So in this case, with the horizontal member and the vertical member, we don't need to memorize even to substitute in this steps. Only for member with inclined angles. But for the horizontal member, we should use the local matrix, it's available. For the vertical member, this member BC, theta x is either it's 90 plus minus. In this case, lambda x equal 0, lambda y equal plus or minus 1. If we go with the global matrix, it will be like local matrix with some arrangement. I will pay your attention during our study. Let's now go to solve examples and find our structure analysis based on matrix analysis method. The proceeding is fixed. We can summarize it. Step 1, we should select our global axis. And for most of the problem, more than 95%, we use horizontal and vertical. So our reference axis now will be horizontal x-axis and the y-axis. The second step, to define the nodes. And the nodes, the concept to define nodes, the start of the structure. You should have here node at A and the node at C. This is, you must have four different direction as a connection. Here you have, you should have a node here. This is the nodes selection criteria. Another selection criteria for EB member, the member have one material and prismatic cross section in our case. But if you have here is steel and here is concrete, different material, in this case you should have a node here. But for the same material, it's no need for any node. So the change of material, you should fix a node in between. Also for the cross section, if you have the cross section here, and here is different sections, you should have nodes. This is not our case, but for the future, if you have different material, different cross section, you should stop at this station and make a node. This is the node selection criteria. In our case, only we have 3 nodes, A and B and C. And this is 2-dimensional frame. That's we only have X force Fx and Fy and the moment. So each node has 3 forces or 3 kinematic. So the size of the system, it's the number of nodes is 3 multiplied by the degree of freedom. It's in our case is 3 multiplied by 3. It's 9. So for this, I expect for the future, our force multiplied by the stiffness matrix. This is the magic equation will be has 9 multiplied by 9 size. Next step, to define the parameter of the members. This is axial stiffness. This is lateral stiffness. This is the element of the stiffness matrix. And just preparation for a calculation. Another point, how to arrange the kinematics. For our side is force equal K multiplied by D. We have the deformation have 2 categories. One is free degree of freedom, like this horizontal movement or the rotation at node A, or the horizontal movement or the vertical movement or rotation. The structure is expected to have this degree of freedom. It's required to calculate it. And at this instant, it's unknown for me. So we call it du unknown. The other parts, the vertical here, deflection, or the horizontal movement, or the vertical movement, the vertical movement or rotation here, or the degree of freedom is known, is well defined, equals 0, and it's called boundary condition, and we call it dk. It's noun. So for the displacement, we have two parts. The same in the forces. We have two parts. One is the reactions. This is a vertical reaction here, and the horizontal reaction at the vertical reaction and rotation moment. And this is how it's required to calculate it. And it's unknown for me. And it's unknown for me. This is, so in this case, we call F unknown. And for the others, the horizontal force here, it's equal 0. The moment here is equal 0. The applied forces here are given, like 5 horizontal force, or vertically, or moment here. This is the external forces, and this is, for me, it's well defined and known for me. So this is both sides of the equation. How to arrange the stiffness matrix to keep this unknown parameters, either displacement or forces, when known displacement and the forces for the solution of the structures. Just one moment. Once we define the stiffness matrix, and we have two sides, either the forces. Now,
Prof, the slide is missing.
Just
the screen, your screen.
Let's go. Is there any problem?
I cannot see your screen. You are sharing Excel, right now?
Sharing just once.
Maybe you can share again.
Let's just moment. In fact, you have the authority to make sharing. I don't have this. The sharing screen is stopped from me.
Can you please try again?
Yes, now it's okay.
Okay.
Now, once we go with the stiffness matrix for the members, we have defined member 1 for the horizontal, and is member 2 for the vertical. And we arrange based on our classification that the displacement, we have two categories. One is displacement, it's known displacement, and the unknown displacement. unknown displacement, it's to be calculated, and the known displacement, it's already given. We will start with the unknown displacement, and in the same order. Usually, we go with x direction, y direction, and the rotation. So we start now with node. This is one, horizontal, vertical. This is rotation, and in the same order, 1, 2, 3. This is unknown. We go with 4 here, and this is 5. So the unknown displacement is now is 5 component, and the other degree of freedom is not known. This is the vertical here, or the 3 degree of freedom, horizontal, vertical, and rotation, and they mainly equal 0. So just to keep in mind this classification of the kinematics or the deformations. So in this case, if we go with the stiffness matrix of the member 1, this is almost horizontal member. So the stiffness matrix, almost it is the local stiffness that we should memorize as here. And we could know that this is the axial deformation in the same direction, horizontal, vertical here, and rotation. This is at the start point. This is horizontal, vertical, and the rotation. And this member, we should define the direction. That means the member we call AB. So the member is a start from A and you go to the B. This is important to measure our angles and to keep the stiffness matrix reservation. So this 3 columns is for the start point. This is for the end point. This is horizontally is the same. This is for the start point. This is for the vertical point. So once we go with the numbers with Young modulus and the E and the L, we get the stiffness matrix like that. But how to define it? This is the member, it's AB. So we concern this is as a local, so it's normal shear bending and also normal shear bending. This is the columns of this 6 by 6 stiffness matrix. But for our global matrix, we have different arrangement. Just we go to rename either the columns or the row. So now we go with the norm, with x-axis. In our case is 4. Then vertical axis. Usually we go this order: horizontal, vertical, rotation. So now is 4, 6, 6, then 5. This is the start point. Then we go to the end point. Horizontal is 1, vertical, horizontal, rotation. The same order is vertical. So this is just renaming the element of the stiffness matrix. We go to the next member. Member one, member two. Member two, it's vertically. So the angle is now is theta minus 90, either for y or x. So we go with the direction cosine lambda x lambda y. And if we go to the global matrix and substitute with this value, we can go with the global stiffness matrix. In this slide, he came from the original. He finds the transformation matrix and it multiplied by the local axis, multiplied by t. But this is a long journey. And I don't prefer to go with this approach because for the vertical member, it's easy to memorize because if we plot here x and y is vertical here and the moment. This is a normal member. The member here have two categories. The normal force, this is one side. And the shear and bending, this is the other side. For the normal, our stiffness is simple, is E A over L. And this term here, come here, say minus, here minus, here is plus. And if we look for the vertical member, the normal force here is sitting in y direction. And so if we try to find here, usually the global stiffness matrix is horizontal, vertical is rotation, horizontal, vertical, here rotation. So if we go with the normal force here and try to make it in the y direction. So if we reserve the y direction here, this y, and this is y, this is vertically. With the same approach horizontally, here, yes, here. This is 4 nodes. It's the normal stiffness. This is E A over L. If we go here, yes. That's E over L, it's 20 thousandths here, yes. This 20 thousandths minus the same value, minus the same value, minus the same. And the normal force reserve all the column by 0, 0 here, 0, 0, 0. So this is vertically and horizontally. That's all for the normal force. Next step, we go to shear force, shear and bending. Shear and bending forces, for the simple case, it's these two terms. That's 12 by EEI over L تقريبا. Just filling the gaps. How to filling the gaps? Here, just This is terms for shear, then bending. This is shear and bending. If we look this stiffness matrix, it's just a rearrangement. That's the normal force coming in the place of shear, and the shear coming to the place of normal force. Here, the normal force go to the normal, and the shear coming to the normal force. This is horizontally and vertically. So if you are sitting in a class with your friend, just changing the seat, then the member here can assign to the degree of freedom. Degree of freedom for the vertical member, this is the vertical member. Here is 1, 2, 3. This is the here is 7, 8, with the same concept, that horizontal, vertical rotation. So 1, 2, 3. Then we go to the end point. It start with 7, 8, 9. It's the same as vertical. This step is called step number 3. Is I memorize, remind you. Our first step is the global axis. Our global axis, X and Y. Second step is the nodes. Third step is the member stiffness matrix. Now we go to the global stiffness matrix. This is, with this equation, is valid for the structure, for the frame. Is the force equal K multiplied by D. We take the stiffness for member 1. This is the horizontal member. And this is the stiffness for the vertical member. And we arrange our kinematic here. This is the red line. Now we try to write this equation. This is for the full structure, all the forces of the structure, but with some arrangement. We start with known forces as a first, then coming with the reactions. In the other side, it's going with the degree of freedom, unknown displacement, and then known displacement that called boundary conditions or supports. And as we arranged it before, so our displacement known is 1, 2, 3, 4, 5. So this is our displacement that should be determined from the analysis. And this is to be determined. Here, 7, or 6, or 8, it is a support or boundary condition or the restraint degree of freedom. That's already now equal 0. This is the kinematics. In the forces side, from 1 to 5, here, this is the forces mostly is known either equal 0 or applied force. In our case, we only have applied force at direction 1 equal 5. And it's both because we have in the x direction, positive x direction. And this is known forces. The other part is unknown, it's forces, and this is the reactions. It's a vertical reaction at the roller, horizontal force, vertical force, moment at the fixed support at the C. This is forces and side. How to build the stiffness? Just the stiffness could be built up using the same order. We have 1, 2, 3, 4, 5. This is the unknown displacement, and this is already fine. We go to the same with the member stiffness and try to assemble. So here is the column 1, and vertically with the same order 1, 2, 3, 1, 2, 3, like with the same number. So if we go this point 1, go in this one, and this cell. This cell it has 2 components. 1 multiplied by 1, because this value for the member 2, if we name it vertically 1, 2, 3, 4, it is the same vertically 1, 2, 3, 4, 5. It's here is 7, here is 8, here is 9. The same order, the same number is the same vertical. So taking this value and drop here, but this number is what the position here is 1 horizontally and 1 vertically. Here, this element also 1 horizontal and 1 vertical and 1 horizontal. So for the global matrix here, this parameter is the summation of all these 2 cells. And if we go down, go down here, we will fill up this from 1 to 3. And the same for 1 and 2 and 3 with the same value. Next, for 4 and 5. 4 and 5. Now, until now, we go with one column number 1, column 1. So column 1, number 1 with 4. Usually, the cell here is K, is I, by 0. I is the row number here. J is the column number. By using this criteria, we can fill in all this value. It's called assembling of K1 and K2. This can be applied for 1 and also for this part. This is string from here. This is 1, 6. This is horizontal. Is the first is 4, then 6, then 5. So this element, if we call the 6, the position is 6, 6, 1. This is the element is 6, 1. The same here. So this will be positioned in the global matrix. Then we go with different elements until we finish the global matrix. This is the stop. This the global matrix. Then finally we get this matrix as a full, based on our classification for forces as known or unknown forces. Known it's from 1 to 5, and unknown from 6 to 9. The same for the displacement from 1 to 5 is unknown and to be determined, and known displacement, it's the support or boundary condition. Our global stiffness matrix can be divided in 4 parts. This is K11. This is this part, and the K21. This is almost, or this is the most 2 parts. And the other 2 parts maybe use letters for the settlement, other deformation, but now we just focus in K11 and K21. K11, it could be used for the determine the unknown displacement. How? If this is the forces, we can get it by multiplying this row with the vertical, like that. But for the known boundary condition, at the support, dk equals 0, dk is equal 0. So our equation will be the qk known forces equal k11 multiplied by du. This is our case. This K11 we know we have it. Who is known for us? It's displacement. It's our target. So this is in the matrix 4. If we go with the inverse of this matrix multiplied by the one, we get the displacement. So now, if we get this part is K11. Here is K11, and this is the forces, known forces, And this is the displacement that I want to calculate. Just go to here, right? This is the displacement. And this is the applied forces. And this is K111. Just I am going with this inverse here, inverse. And once I make this inverse multiplied by the force here, I will get directly the displacement. It's now the displacement. That's mean D1 here, it means the horizontal movement. D2 is the vertical deflection here, and is with the same meaning. This step is called solve for the displacement. So our stiffness matrix is called displacement methods because our first step, our outcomes is the displacement. Secondary is the reactions. As we come back to here is the second equation. This is the force, the reactions that I am looking to get. I can get it by multiplying this row by this vertical row, and I get this equation. And now dk is supports, so it's zero or boundary conditions. So K22 is not active at this moment. So the known forces now is a function of K21 multiplied by du. That I get it from my previous step. Yeah, that's here. So now I got K22 here. It's this bar, and to calculate the reactions. Here, this 6. This is the reactions, vertical reaction here. The 6 horizontal, vertical. This is, and this is the moment. This is 6, 7, 8, 9. This is, and we already have here the displacement from our previous steps multiplied by K2. Directly we get the reactions. Same, that's mean here is minus. Here is minus. Sorry. Here is minus. That's we in our previous we just moment. We assumed horizontal and vertical axis, and this is our positive directions. So once we get this is minus, that's mean it's downward, and here is -6, -5. That's mean negative x direction. So that's 5 here. Then 1.87 positive, it's over, and this is the moment. Even during all our step, we don't mention any equilibrium, but it's the equilibrium condition, and the compatibility of displacement is built in the stiffness matrix. Now, if we go to check the equilibrium, the summation of forces in x-axis directions, we have applied force here phi, and hence the reaction is phi in the opposite direction, so it's equal 0. Also, the equilibrium in the vertical direction here is minus downward. Here is vertical in the summation is equal 0. And if we go with the moment at any point, either A or B or any point, summation moment should be equal 0 in this case. And we go in the right direction for the solution, either for the displacement or the reaction. This is the first step of our structure analysis, to find displacement or deformations and the reactions. Second step is to find the internal forces, and this is for the design as a next step for the analysis. And this is easy, just going with the stiffness matrix multiplied by the kinematics of the member, either calculated or boundary conditions. And the problem now, what is the stiffness we use? It's global stiffness or local stiffness? Usually, for the design, we need the normal and the shear and the moment directly, not the global stiffness. So in this case, if we have a member in general case, if we multiply the stiffness multiplied by the displacement, that's horizontal and the vertical and the rotation, and the global stiffness that we use it. If we multiply it by D, we will get the straining action of the member. It's called the normal force, the horizontal force, vertical, and moment at the start and the end. It's easy to use it for the horizontal and the vertical member. However, for general member, I will get horizontal force, vertical force, and moment like that. So you need to make another step effort to change it to a normal force along the member and a shear force along the transverse direction. And the moment it will be the same. This is the concern for general member. But for the horizontal member or the vertical member, that's a special case. So it's easy for us, just multiply the stiffness matrix multiplied by D. So in this case, I will get forces horizontal, vertical, and the moment. In our case, for a horizontal force here, for member 1, it will be normal force. However, for member 2, it will be shear force. The same for vertical force. For member 1, it will be shear. However, for member 2 will be normal force. Once we have 2 members or 5, whatever the number, I can go to find the internal forces, normal shear moment, and then we can go with drawing shear force diagram and depending and moment. Then we can proceed to the design. This is the matrix, stiffness matrix. And this is standard or systematic proceeding to make the full analysis, either for deformations or reactions or thermal forces. And it can be applied for beams or frames or trusses. In this case, this is the case for frames. And I try to be the same in my technical terms and the solution proceeding with the textbook of Hebler. But the Hebler I have some concern about how to arrange the degree. It's the presentation is okay. Dr. Suhaila?
Yeah. So actually, it is a very good lecture given by Prof. Shata. I believe students also learn a lot about actually about the derivation of the stiffness matrix at the beginning of the process, and how we solve the displacement and the forces whenever the unknown displacement is more than 3. And the solution that you have shown just now, based on the matrix, inverse matrix, right? So solve in Excel. Okay, the one that we actually don't touch before. So Dr. Sophian, do you have any question to ask, or students, do you have any question to ask the professor before we end session?
So far, no.
You are welcome.
Okay. So far, there is no questions. Happy to attend your lecture, Prof. You may continue, Prof.
Actually, I think we have set 2 hours, this session for 2 hours. That is why Prof. Shata stopped just nice time. So do you want to add anything, Prof?
Just one point. Here, just for Hebler concept.
Yeah.
Just sharing the presentation, it's okay.
It's okay.
The key for Hebler for Hebler, it's have his background as a hand calculation. What does this mean? For our frame here, it's 2 members. So it's easy to numbering the known degree of freedom or unknown degree of freedom. But for a big number frames, it will be difficult for us to arrange this degree of freedom and the numbering the red degree of freedom and the black ones. And also, this is one point. Another, once we write the stiffness matrix, each member, the problem when we go to the overall stiffness matrix. It's tedious or complex to build the stiffness matrix. You should pick up element by element or small groups. And this is for only 2-member frame. But for a high number of members, it will be difficult to follow up this approach for building the stiffness matrix. In my class, I teach it in different way. And also this approach cannot be followed by computer or commercial software because you have mankind definition of the degree freedom or arrangement. So in our case, we try to automate it. So in this case, our solution with different approach could be start from here, just with the same problem, just define the global axis, and we agree it's mostly horizontal and vertical axis. Then we go to the nodes, and we explain the concept of the selection of the nodes. Usually the gates or the structure, ends of the structure should be nodes. So here should be node, here should be node. The change of the direction should be node. If you have a material change or cross-section change, you should have a station and make a node. This is our nodes. Once you define the nodes, the number of nodes, and we go with the frame, so our degree freedom is horizontal, vertical rotation. So we concern in our 2-dimensional frame with the 3-degree freedom, and we have 3 nodes. So our system is 9 by 9. So its force is equal K multiplied by D is 9 by 9. Stiffness matrix 9 by 9, and also the displacement is 9 multiplied 1, and here is the force is 9 multiplied 9. Then next step we go with the member. Member 1 is the horizontal one here, and the member 2 is the vertical one. And we write the stiffness normally as we explained in the previous approach. Is for the member 1 and for the member 2. And here I just pay your attention here that the horizontal member and the vertical member is a special case of the frame structure. So for the horizontal, the global matrix is the same as the horizontal matrix. So we concern with horizontal, vertical, and the rotational. This is at the start point, horizontal, vertical, rotational. This is the 6 degree, 6, 1, 2, 3, 4, 5. For the horizontal member is normal force is horizontal. So this is row 1 and the row 4, and the column 1 here and the column 4. This is 2 columns and the 2 row is reserved for horizontal, for axial stiffness, and the other slots is shear and bending. For the vertical member, if you focus and you look carefully, the stiffness matrix is almost the same because this is the same number, the same material, the same length, cross section, but arrangement. If we change the shear and the bending, just changing the seats, so I will go stiffness 2. So just pay attention to my student, that the vertical member and the horizontal member, it's easy to memorize without referring to the global stiffness matrix and any angles or any troubles of substitution and the transformation or something. Only the general member will be difficult to build up the global stiffness. Then once we get the stiffness for each member, it may be 2 or 5 or 10, whatever the numbers, I try to build my systems without arrangement of the degree of freedom. The degree of freedom is automatically assigned because we have 3 degrees of freedom: horizontal, vertical, and rotations, based on the node number. So this is well reserved 1 and 2 and 3. Then this is 4, 5, 6. Automatically this one, and then horizontal, vertical. So in this case, the force vector will be, this is for node 1, horizontal vertical moment, for node 2, for node 3, this is horizontal vertical. The same here, horizontal displacement for node 1, node 3, node 2, and node 3. In this case, I will take all this block 1 times. It coming here, here. This is around 36 element. One movement, it's enough. It's enough with that. Then I go to the member 2 because this member 1 is connected 1 up to the one is reserved 3, and this is for 2. There's the same here vertically. This is 1 and this 3. If we go to reserved seats, so and this is for 1. This is for 2. This is for 3. Also, horizontally is the same. So if we go with this matrix, it will be coming here. It will be coming here. Yes. For the member 2, with the same approach, but this member is from 2 up to 3. From 2 up to 3. So, and 2 have this 3 columns here, strands. That's the same horizontally. So if we go with all this block here, move 1 time, it will come. It's coming here. You can compare the number. You will find here overlapping area. This overlapping area, if you focus it, it's 2 horizontally and 2 vertical. Why? Because 2 is connected to member 1 and member 2. Just here, the summation of the overlapping. So this is the stiffness equation with easy assembly. And then this is with easy ascent. That's our last. Now just we look at the forces and look at the kinematics displacement. Kinematics, we know that for the kinematic, with the same order, we have the vertical here, the horizontal is unknown, for the vertical is known here, so equal 0 here, equal 0. Then rotation is unknown, so it's still here. But for horizontal, vertical rotation, it's unknown. But for at the node 3, it's all are boundary condition, so equal 0. So here is it's a boundary condition. And the other is known, so the horizontal displacement here, or the horizontal displacement here, or the vertical, or the rotation that have here, one, and this is unknown. In the other side, I classify the forces, Fx1 moment and 2, and this is all are known and given force, while the black one is the reaction and need to be calculated. I will start arrangement from here, just changing the seats. I will try to make first the kinematic here with the same order. For the kinematic here, this horizontal at 1, rotation at 1, horizontal at 2, vertical at 2, and the rotation at 2. Just how to, just I take this, just one moment. Now this row at the first, it is the same here. I'm trying to collecting the unknown kinematics with the same orders. So first kinematics is the horizontal displacement. The second is the rotation. So I go this row, or this, and coming to the second seat here for all along all the horizontal. Then the same horizontal, vertical, horizontal, and coming all of them here. All the row is just shifting up and bringing the down, bring. Just one moment. And bringing this down. This is, we call it arrange rows. Just shifting between rows to keep the kinematic beside each others and the reaction beside each others. But you keep in mind the same you did with the row will be done for the columns. For the columns. In our case, we start with F1, this horizontal rotation in this one, and horizontal rotation and the kind of that we have did here in row arrangement. We should make it as column arrangement. For the horizontal here, it is the same, so it will be the same. Rotation here, it's in the original matrix is horizontal, vertical. So this will coming in the second one. So it's will coming. This is coming after. This is coming after. This is coming after. With the same arrangement. Just keeping the column of kinematics unknown in the same order. Finally, we get the stiffness matrix with 4 parts as we defined before. Here, next step. Just a moment.
Actually, the letter that you have you are showing now is actually part of finite element method. Student will learn this in the next semester.
It's okay. Sorry. 5 minutes and I finish.
Yeah. Okay.
By this approach, I will get the stiffness matrix in 4 parts, as we know before, as this approach. And then I continue with the same proceeding, that how to determine the displacement as a first step, and then reaction, then the internal forces. This is the reactions, the displacement. K11, it's what taking in this, taking K11, so in this bar, and this is the force vector, and this is the unknown displacement, just K11 and the inverse. Then we get the kinematic unknowns. Next, after we go with the same reaction, K22, and this is the stiffness matrix multiplied by the displacement that we got it from the previous steps. Multiplying these two matrices, we get the reactions. The main difference between this approach and the last one, and I assemble the stiffness matrix before arranging the kinematics. And this is automated, can be done by the computerized for big numbers with any mankind and arrangement. After that, based on the boundary conditions, I try to arrange the stiffness matrix after assembly, not before, to make it a systematics. Just we arranging the rows as a first, as a one step, then arranging the column with the same order in the previous steps. In this case, we will get the 4 bars of the stiffness matrix based on usually we use K11 or K22, and this is the other 2 bars can be used for another point. Then we go with the same proceeding, just the assembly of the overall stiffness matrix and arrangement for the kinematics. Our Hebler approach, you should have some hand or some efforts to arrange and then assembly, and for big structure it will be difficult. But in our approach, just the kinematics of the member depending on the node numbers, it's equal the degree of freedom multiplied by node, and I assemble the stiffness matrix without degree of freedom, because so this is have more advantage. If I have this frame with a slight change, just change the roller to hinge, for the Hebler it will make a lot of disturbance. But for our case, just changing the assembly and the arranging column and the beams. So finally, we get the same solution with more saving some efforts. And you have the choice to follow what's the best for you. And this is almost the matrix analysis for frame for a given loads. There is indirect loads maybe in another lecture. So I thank you for your attention and for your time, and it's my pleasure to keep contact with you, and I hope you could get some skills about matrix analysis from, and sometimes the online not so perfect, but however I try to make more easy. Thanks for it.
Okay, before we end session today, I would like to take some photo. So, Prof, can you please stop sharing first, so that we can have photo session. Okay, I invite all students to switch on your camera for our photo session. Prof, can you please stop sharing first, Prof? Stop share the slide, the screen, your screen. Stop sharing.
Screen, yes, just.
Yeah.
It's okay now?
Yeah, it's good. Wait.
Assalamualaikum.
Waalaikumsalam. Okay, wait. Okay, okay, we take the first one. Okay, 1, 2, 3. Okay, another one. Okay, wait, I change to together mode. Okay, get ready, get ready. Get ready, everyone. 1, 2, 3. Maybe the last one. Wait, yeah. Okay, 1, 1, 2, 3. Sorry. Another one, the last one. Sorry. Okay, another one. Okay, this one is good. Okay, get ready. 1, 2, 3. Okay, I will share to all of you the photo after this session. Okay, Prof, can wait. Okay, I would like to express my appreciation and blessed to have Professor Shahata from ASU University from Egypt, from Egypt to our class. Okay, now in Malaysia is 10:20 night, Prof. So what is your
Yes.
time there?
Now it's
What?
4 o'clock and a half.
Oh, I see. So evening, right? Okay, I hope maybe this is not the first and the last. Inshallah, we will continue this
Inshallah.
collaboration after this. So I am very happy. So actually we have planned this since last semester, and Alhamdulillah. So this time we can proceed with this session. I hope whatever you have shared, student can actually maybe you learn something new tonight, but don't worry because a structure analysis that you will learn this semester is not the end of structure analysis, because next semester you have to take another structure engineering structure courses such as finite element, which is inside numerical, and you will at that time you find that whatever that Prof have shared is actually valuable for you. Okay, before we end session, Dr. Sofian.
It's okay. Okay.
For me, it's very interesting lecture actually, Prof. So I like your second approach actually. Very interesting. So hopefully that we can continue our second lecture or third lecture on our structure analysis maybe next semester. So hopefully this one will continue our what we call that, our relationship between both universities. Thank you very much, Prof.
Okay, thanks. It's my pleasure to continue, inshallah, for the next semester. In fact, I know Dr. Suhaila from a long time ago. It's our pleasure to start our cooperations, especially in teaching or even research or undergraduate or postgraduate cooperations. We have different classes. even your student can contact for if they have any inquiries or need more explanation during their off time from class. It will be my pleasure to keep this kind of classes or lectures. It will be nice. And thanks for your attendance and this chance.
Yeah, Prof. Maybe we can start our research collaboration after this, inshallah. Maybe Dr. Sophia also want to join. Okay. Okay. Before we end, students, do you want to say something before we end session? Anyone? We have actually about 80 students join tonight in this session. Okay, if don't have, so I think we can stop after this, but I hope that we can proceed with the next session. We will make the formal procedure, follow the formal procedure, inshallah. So maybe we can invite our head of department as well. But this time, this is just like ad hoc session, like let's say ad hoc session, because we have actually set different date, right? Last year, but we cannot proceed with that one. So alhamdulillah, we actually finally success in managing this session. Okay, so I would like to thank everyone, student who joined this session. Hopefully this will benefit you, inshallah. And to Dr. Sofian, thank you for joining and wait until the end of session. So thank you, Professor Shata. I'm very happy for this collaboration, and inshallah we will continue in the next session. So thank you very much. Inshallah we will meet again. Ya, Assalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum. Thank you, Prof.
Thank you, Doctor.
Thank you, Doctor. Thank you, Prof.
Thank you,
Shukran
Prof.
jazilan.
Thank you, Doctor.
Thank you, Prof.
Thank you,
Have a nice
Doctor.
day.
Thank you all.
Shukran
Thank you.
Bye bye, Doctor.
Thank you, Doctor.
Thank you, Prof.
Doctor.
Shukran.
Okay, thank you very much, Prof. Assalamualaikum.
Salam. Okay, so thank you very much all. I will end the session. Waalaikumsalam warahmatullahi.